Hello, in this lecture we are going to look at the runway length corrections which have to be applied to estimate the runway length required by an aircraft when operating under non-standard conditions. Now, all runways are not located at mean sea level, they are also not on perfectly level ground, and finally they also have temperatures and pressures which could be different from the ones which are expected in the ambient conditions under ISA. Now, what to do in this case? We need to apply corrections to take care of all these three non-standard operations. So, we are looking at three corrections to be done to the basic runway length. Now, this is not about declared distances, this is about whatever length is required by the aircraft. So, when the pilot knows that there is so much TORA, TODA, ASDA, ELDA, you have to also calculate how much I need, and what I need based on these three off standard conditions should be less than what is available, otherwise I cannot operate. So, that is why it is important to know what corrections to make. So, we make corrections in an order. First we correct for elevation or the airport at a height other than mean sea level. After that we do the additional correction for temperature, that is, if the temperature at the airport is higher than what is expected at that altitude under the ISA conditions or the standard conditions, and then lastly we do the corrections for the gradient, because runway need not be flat. Okay, runway is spread over a very long distance. It is very difficult to expect that the civil engineers will make it perfectly flat like a table. No, there will be some undulations and they are natural. Sometimes there are very large undulations, but what to do? You need to accommodate with that. Of course, it makes a difference, as we can see, to the runway length available. So, we do it in this order. First we do the correction for elevation, then we add the temperature correction, and then we add the gradient correction. So, let us see. Here is an example of an airport which is above the mean sea level at an altitude h. So, the basic runway length at mean sea level is BRL, and BRL subscript E is the basic runway length required because of elevation. BRL E will be always more than BRL. Because any height above the mean sea level definitely makes you to require a larger runway. Why? Because elevation has an effect. It affects the ambient temperature, temperature falls and pressure also reduces, plus the air density also changes, and because of that, the temperature and the pressure and the density, they all affect the aerodynamic forces. So, therefore, you need higher runway length. Remember, always an airport at a higher altitude will require a larger runway length compared to one at the lower altitude or the mean sea level. Okay. So, the correction recommended by ICAO is that for every 300 meters increase in the altitude above the mean sea level, you must add 7% to the runway length required. So, remember this, 7% for every 300 meters or about 1000 feet. Okay. So, if you are at 5000 feet, then 35% more. Let us revise ISA. In ISA, we know that now this is ISA, the other two are non-standard conditions. So, this is our ISA. So, under ISA conditions, we see that the temperature falls linearly or is assumed to fall linearly at 6.5 degrees per kilometer up to 11 kilometer, and then it remains constant. Now, we do not normally have airports above a height of 11 kilometers, so let us not worry about those few airports. Let us worry about most airports which are only located below 10 kilometer altitude above mean sea level. So, there is a linear reduction of 6.5 degree per kilometer, right. Pressure at mean sea level is 760 millimeters of mercury, 29 inches of mercury. This can also change from place to place. Air density also is standard, but it will also change when you have a higher altitude. Now, let us look at temperature correction. Now, the temperature at sea level under the mean conditions is 15 degrees centigrade to 88.16 degrees Kelvin, right. So, at a elevation, the temperature STE, standard temperature at the elevation, it will be T at mean sea level plus delta T by delta Z, which is the lapse ratio divided by the altitude into the altitude, which is the Z value. So, there is something called as a airport reference temperature or ART. Now, temperature does not remain same throughout the month, throughout the year, even on a daily basis there is a change. So, we have something called as ART, which is the airport or aerodrome reference temperature. This is equal to T1 plus T2 minus T1 time divided by 3. What is that? T1 is the monthly mean of average daily temperature for the hottest month of the year. So, what you do is identify the hottest month, the month during which the temperatures are the highest, and in that month take the mean of the average daily temperature, that value is T1. And what is T2? T2 is the monthly mean of the maximum daily temperature for the same month, right. So, during that month there will be some maximum temperature, right. So, T1 looks at average daily temperature and T2 looks at the maximum daily temperature, and using this formula you get the value of ART. Now, the guideline from ICAO is that the correction for the temperature should be 1% increase in the runway length for 1% rise, 1 degree centigrade rise in the ART above the ISA temperature at STE. So, therefore, what you do is first you calculate what is the temperature at that altitude under ISA conditions, then you calculate ART, and for every 1% higher value of ART compared to the standard temperature expected under ISA, you have to add 1% to the runway length. So, if you have 10%, 10 degrees higher temperature, in 10 degrees higher ART, you have to have 10% more runway length. Okay. Now, ICAO also recommends that the correction because of these two should not be more than 35%. If that is the case, then you have to do a lot of testing on the runway, and you have to, you do not go by this, then you go by actual values of how much runway is required. So, ensure that or check that the correction because of elevation and temperature should not be more than 35%. Okay. Now, we look at the third aspect, which is the runway. As you can see in this picture, runway gradient. This is a picture of an airport runway, and you can see it is not flat. You can see that it is wavy. Okay. This is almost the case in all runways. Okay. It is very difficult to make the ground completely flat because that will be very expensive. So, there is something called as a gradient correction. What is that? Now, gradient is also two types. There is a transverse gradient. This is provided so that the water can be removed during monsoon or during collection. So, there is some slope at both the ends. You also have longitudinal gradient, which, as you can see in this picture, is there simply because of the site considerations. Okay. So, the effect of steep longitudinal gradient. Now, we will not worry about transverse gradient right now. We will talk about longitudinal gradient only. It has got a major effect. It will either it will go for premature liftoff, okay, or it will create structural defects on the aircraft. Plus, there will be higher consumption of energy during the takeoff, and therefore, you will require longer runway. So, the effective long gradient or ELG, that is equal to the runway elevation max minus runway elevation minimum divided by total runway length. That is the definition of effective longitudinal gradient or effective long gradient. So, G correction is very severe. It says for every 1% value of the effective longitudinal gradient, you need to add 20% to the runway length that is needed. So, let us look at one example, okay, just a theoretical example to make it clear to you. So, there is an airport, theoretical airport, at which the basic runway length is 1600 meters. This is the runway length required at mean sea level, ISA conditions, flat runway. But at this airport, the elevation is 125 meters above the mean sea level, and the temperature, reference temperature ART is 25 degrees centigrade. Okay. So, now, and this is the value of the gradient. So, this airport, if you divide it into these segments, you will find there is 1% gradient positive for the first 300 meters, then the next 600 meters it is minus 0.2, next it is plus 0.5, next it is 1%, and finally it is 0.3%. Okay? So, this is the value given. Now, our job is to estimate the corrections required to this basic length of 1600 meters. So, first we will do the elevation correction. Given that BRL is 1600, E is 125 and ART is 25. So, we know that the correction that is to be given is 7% per 300 meter rise above the mean sea level. So, we have 1600 as the baseline value, we have 7% and we have 125 meters elevation compared to 300 meters. So, for 300 meters it will be 7 by 100. So, this value now you need to calculate. Now, wherever you see these three red colored question marks in the presentation that follows, you need to pause the video and do the calculation, get the number. Remember, when you do a tutorial yourself, that is the time when you really understand, otherwise it goes above the head. So, listeners, my request to you is pause the video here, do this calculation, and then I will show you the number, compare with my numbers. There could be errors. If there are any errors, please report to us and we can correct our presentations later. So, please calculate. Now, my value is 46.7 meters. So, therefore, the basic runway length corrected for elevation effects will be the basic runway length plus LE. So, the BRL is 1600 and the correction is 46.7. So, therefore, please add these numbers and get the value of BRL subscript E. That value is 1646.7 meters. Okay. So, remember now the runway length corrected for elevation from 1600 is 1646.7, not much, okay, not much, but still it is there. This becomes our baseline for the next correction. Now, for the temperature correction, we are given that ART is 25 degrees centigrade, E was 125 meters, and we have just calculated the LE to be 1646.7. Now, the ST will be equal to the T at the mean sea level plus the lapse rate upon the altitude into the altitude value. So, this we all know, sea level is 15 degrees, lapse rate is 6.5 degrees per kilometer or 0.0065 degrees per meter, and the altitude is given as 125 meters. So, please calculate the value of STE, standard temperature, at 125 meters. This is 14.2 degrees centigrade. So, the temperature should be 14.2 degrees if you are at 125 meters above mean sea level, but the temperature is 25 degrees. So, therefore, the rise in the T is ART 25 minus 14.2. How much is that? Please calculate. Pause the video, calculate. That number according to me is 10.8 degrees centigrade. So, this runway is having a surface temperature higher by 10.8 degrees compared to what would be there under standard conditions of ISA. Now, we know that we have to increase the runway length by 1% for every 1 degree rise in ART above ST, and here it is 10.8 degrees. So, therefore, we need to increase the runway length by the base value, not 1600 by the way, the LE value should be used, because we are doing the correction sequentially, first for elevation, then for temperature, then for gradient. Okay. So, that is 1646.7 into 1% or 1 by 100 into 10.8. What is the value? The value comes out to be 177.8 meters. So, you require around 178 meters runway extra because it is at a hot location. Hence, the corrected length will be the length 1646.7 plus this additional value 1778.8. How much is that? Please calculate. That value is 1824.5 meters. So, now this becomes our baseline for the next correction, 1824.5 meters. Finally, we look at, before we do the gradient check, we should do the ICAO check, right. What is the ICAO check? The correction because of E and T should be not more than 35%. So, our value is 1824.5 against the baseline of 1600, and if you look at a percentage, it comes to be 14.03%, right, which is lower than 35%. So, we are on the right track, we do not have to do anything, we can accept these values. Now, let us go to the last correction, which is the gradient correction. So, here we have some data, how much is the rise or fall. Okay. So, this airport, if you look at the runway from starting point 0 to 1800, so the first 300 meters you have a plus 1% gradient as shown in the bottom. So, here the rise in the runway is 3 meters. Then the next one, the next portion from 300 to 900, there is a minus 0.2 gradient. So, therefore, the change will be 1.2 degrees, 1.2 meters. So, therefore, this 3 will become 3 minus 1.2, that is a lowering, that will become 1.8 meters. Okay. So, the runway was 3 meters high at the end of 300 meters on an average. It has come down to 1.8 meters at the height of 900. Then the next one is 900 to 1500, the runway is having a gradient of plus 0.5%, that translates to 3 meters. So, 1.8 has now to be increased by 3, so it will become 4.8 meters. Now, runway is on an average 4.8 meters high at that point. For the next one is having a plus 1% gradient. So, over 300 meters from 900 to 1500 to 1800, it will become 3 meters. So, it will further increase from 4.8 to 7.8 meters high. And then we have the next segment, which is from 1800 to 2000. There it is 0.3, so that will be reduced by 0.9, so it will become 6.9. So, this is how the height of the runway would be, okay, as you go along the length. So, now we know that the basic runway length corrected from the elevation and temperature is 1824.5. So, the ELG value will be the runway elevation max, which is 7.8, minus runway elevation minimum, which is 1.8, divided by the runway length. Okay. In fact, it is 0, sorry, not 1.8, it is 0 at the beginning. So, it is 7.8 minus 0 by 1824.5 into 100. This turns out to be how much? Please calculate this value, the value of ELG, the elevation, and it comes out to be 0.4275%. So, the correction is 20% for every 1% ELG. Our case it is only point. So, so that will become 1824.5 into 20 by 100 into 0.4275 by 1. So, that will be how much? Please calculate. This number will come out to be 156 meters approximately. So, we need to add 156 meters because of the gradient at the runway. So, the BRL, basic runway length from elevation, temperature and gradient, will be equal to BRL ET plus LG. It was 1824.5, we have to add 156 meters. Please calculate the value of this. You will find that the number is 1980.5 meters. So, if you require a runway of 1600 meters at standard conditions, elevation at mean sea level, temperature equal to 15 degrees centigrade at mean sea level, and completely flat runway, you would require 1600, but at this airport you require 1980 meters. Let us do a last check on the summary. So, BRL was 1600, altitude was 125 and ART was 25 degrees centigrade. So, the delta L from elevation was 46.67, hence the BRLE was 1646.7. To that we have to add 177.8 because of the delta L from ART. So, the ERT became 1824.5. To that we have to add the extra length required for gradient, which was 126.94 meters, hence BRL will become 1980.5 meters. So, finally, the percentage increase in the BRL is from 1600 to 1900 divided by 100. This is the percent. Please calculate this number. This number is 23.8%. So, in other words, the runway length has to be increased by almost 23.8, 24%, 25% almost because of these 3 corrections. Okay. Now remember, although in this particular lecture I have solved a tutorial for the determination of the corrections, but I have not solved the tutorial for declared distances. In fact, I have only shown you an example for one airport, the Mumbai airport, but there is a detailed tutorial on calculation of declared distances for one theoretical airport. So please watch that tutorial after you watch this video to improve your understanding. Okay. Thank you so much for your attention.